right, thank you so much for the introduction. Hello everyone, thank you for joining me this session where we're gonna take a sneak peek into how neural networks try to make sense of the world. The reason why I choose this topic, or why I think it's important, is that the fact is that the AI tools are all around today. And I believe that most of us are making sense or making use of them like on daily basis. And I also think that in order to understand those tooling, it's important to understand what drives them, what's inside, what is the very core concept of these tools. And the journey begins with artificial neural network. So the goal of this session is not just theory for theory's sake, but it's mainly about understanding how neural networks work and use that as a valuable context when trying to think about today's AI tools in general. All right, so before we're going to dive into the topic, let me just very briefly introduce myself. My name is Vojte. Koz uch. I'm working as a senior software engineer at Muse. Muse is a hospitality platform. You might be wondering what exactly that means. We're trying to support our customers on their journey to provide as best experience to their visitors, customers as possible. We also try to help them on their mission to drive profitability with the appropriate tooling, and also in general we try to streamline the operations, save some time from the staff so that they can use it more effectively, ideally spending with the visitors coming to the hotel or any other property. Before joining Muse this summer, I worked mainly in e-commerce and ticketing, hence the second line on the slide. And finally, I've been into AI and machine learning pretty much since my college days. And as a fun fact, I spent those days here at this very uni. All right, so now let's go straight into the topic itself. We're going to start with some analogy where the inspiration for artificial neural networks actually came from. We're going to look into the math behind the mathematical model itself. Also, we're going to mention which kind of data we can actually use. We can use to feed the neural networks, and in general, how to shape the data in order to get some sensible, useful output from them. We're going to look into one of the neurons that make the main unit of the whole system. Then we will spend some time on the training phase itself to understand how we can actually make our neural networks to learn something. And we're going to wrap things up with the demo. So starting with the inspiration, the motivation, you can look for the answer where this inspiration came from, literally inside your head. I mean, you can't really, but hopefully got the idea, as the fundamental concept has been taken from or inspired by the biological analogies. Inside our brains, as we as human beings have, there are entities called dendrites. And these entities are responsible for transmitting electrical impulses. And then there are neurons, as you can see in this picture, such as this one, for instance, that can then receive the signal, and they can decide whether they're going to pass on the signal on another neuron or stop it from being transferred or somehow limit it. And that's the main idea of the whole concept. It's important to say that this mathematical representation, it's just a simplified version of this biological motivation, as once the fundamental concept was established, the rest of the development continued completely independently of the original biological analogy. So we can say that the artificial neural networks are just simplified models of that inspiration, and often quite distant from the original inspiration. All right, so now it's time to look into the mathematical model itself. And as you can see, hopefully this picture looks way less complex than the previous one. What we can see in this picture is like a sample of an artificial neural network. You can look at that as a kind of graph. There are some nodes of 3 different colors. I'm going to explain in a sec. And those nodes are interconnected by some edges. And each of this edge has a figure, a number attached. This like W. This is attached to each of those edges in there. And those weights, getting back to the biological motivation, represents how, of what importance that particular signal in between those 2 neurons is. And at the same time, it's a fine-tuning parameter that we can use to adjust in the process of learning or training to actually try to get some better results out of our neural network. We're going to get to that in a minute. Now, let me just briefly explain to you those 3 different colors. In general, the signal is being transmitted from the left-hand side to the right-hand side. So the first layer, the gray one in here, it's the so-called input layer. This is where the input data is being received. So depending on what is the domain of the input data, we need to have accordingly set the number of neurons in here. Then we've got a so-called hidden layer, which is the like dark blue or black color in here. For the sake of the sample, we've got just one hidden layer in here, but usually it's many of them in the like real-world scenarios. There are like tens or even hundreds or thousands of them. And finally, we've got the output layer, which is the light blue one in here. And this is where the output is being emitted. So depending on what's being received on the input, at the input side, is then being emitted at the output side. And again, the dimension, the number of neurons at the output is equal to the dimension of the outcome expected. So we just introduced to ourselves the structure, the architecture of neural network. And while it's quite important to get the structure right as well when trying to build some kind of solution with neural networks, what I think is even more important is to have quality data that are sensible. I mean, obviously, the data needs to be, as I said, sensible and machine readable. But we also need to think of or keep in mind the fact that neural networks cannot perceive like real-world entities the way we do. So imagine an example of object detection. Let's say we have some images, and one of them is of a soccer ball. And our goal is to predict what kind of shape the soccer ball is in the like 2D dimension. So our options are square, triangle, circle. And even though we as human beings can see the image, the same doesn't apply to the neural network. So for the neural network, it's just some kind of representation of some figures, some numbers, some set of those. And the goal in that case is basically to somehow force, let's say, or push the neural network to emit similar output that is like sensible for us for similar input. So if there are 2 similar images of a soccer ball, our goal is to get the same output, which should ideally be the circle, for both of them. And on that mission to prepare the data before actually start working with them, there are quite a few practices being performed. I'm mentioning just a few of them, so I'll just very briefly go through those so we can get a better idea of what exactly needs to happen before we're going to dive into feeding the neural network and start training it. One of those is handling missing values. Imagine the input data as a kind of Excel spreadsheet where we've got like tens of columns, so-called features in this context, and like some rows that represent the individual object. And it can happen, then here and there is an empty cell. Some data are simply missing. And the problem is that the neural network cannot really think of what are our intention and think of what should be the missing data replaced with. So it's our task, it's our responsibility to make sure that there are no missing features or missing data at the input. And one of those options is to simply remove those columns or rows where the data is missing. Another is to replace it with some standard values such as average, mean, and so on. Another important fact is that our neural network can work quite well in the training process. We can be achieving like great results, great accuracy, but it may happen that the same is not gonna be the case for the object not yet seen by the neural network, like the production usage, we can say. And in order to prevent this from happening, we can split the data set into two, like training and testing, and use the portion of the data that we allocated for the testing part just to validate that our model works the way we perceive or we expect it should work before actually like deploying the model and considering it being ready for the production. Normalizing, standardizing, it's not uncommon that the values of the figures, like again, imagine that huge spreadsheet of some data, the values in there can diverge from minus infinity to plus infinity. And if there are if the scale is like too high or too great or too big, this introduces unnecessary complexity. And our goal is usually to reduce this kind of complexity as much as possible. So scaling those to some set feature and limiting this the size of the scale can help us with reducing those problems. And finally, encoding. For that, I prepared this image. Again, as I said at the beginning, the neural network cannot really perceive the real-world entities the way we do. So we cannot really say, this is a square, this is a circle, this is a triangle, or mark it as one of the features. We need to somehow transform it to the numeric representation. And you could say that these two examples are basically the same and could mean the same, and it doesn't really matter which one we're going to use. But there is indeed a difference. Because in this example, which is called label encoding, just for the context, this one is called one-hot encoding. So in the label encoding, you can see that we are using numbers like 1, 2, 3. And the problem that may happen is that the neural network gonna start seeing some kind of pattern in terms of ordering. So it may happen that you're gonna end up with results like triangle is greater than square, or circle is greater than square, or square is less than circle because 3 is greater than 1, and so on and so forth. So just why I'm showing you this very specific example to give you some kind of idea what all needs to happen before we actually gonna start training our neural network. And it's being said quite often that your neural network is only as good as your data is. All right, so now let's take a look into one of those neurons that are making up the whole network. And you may be surprised that there is actually not that much happening, or it's not like rocket science. There are basically two tasks being made or performed by the neuron. The first one is basically just a sum of the input. As we said, each of those inputs has a value attached to weight. So we're basically doing just weighted sum of those values. And so we get some number. And in the second part, we need to decide whether we're gonna, let's say, activate or fire the neuron or not. So again, let's get back to the biological motivation or inspiration. The neuron, in that case, can also decide whether you're gonna pass the signal on another layer or not, or stop it from being received. For that purpose, we have two entities in here. Activation function you can understand as a kind of filter. So there is a number at the input, and the outcome is some standardized, normalized value, indicating how much actually, to what extent we wanna fire the value from the neuron. And there is also a bias, which is a value that you can see as an indicator of how tricky it is to achieve that yes or no at the output of the neuron. Imagine that your neural network tends to say no too much or too easily, and you want to somehow push it to try to say yes a bit more in order to support the exploration, and because eventually the neural network can actually see that sometimes saying yes is better than saying no. And that's exactly why we got this kind of feature or parameter in place that we can also fine-tune in the process of training the neural network. So now let's take a look into the training or learning phase itself. Important fact is that each neural network, even the simplest one, start like completely randomized. All those values, all those parameters are just random values. We don't have any shortcuts, any rules to what value we should set those. So it's just like a random set of numbers. So even the simplest neural network has to undergo hundreds or thousands of iterations of adjustments in order to start getting some sensible outcome from them. So the first run from the neural network is usually a nonsense that doesn't really make sense, and we need to fix that. At this picture, we can see the same neural network again. Just for the sake of simplification, I replaced those 4 neurons with this one single neuron that indicates the outcome in general, which is like a set of numbers. And we're going to talk about backpropagation. Backpropagation is an example of so-called supervised learning methods. In the supervised learning, it's important to know that each input has a label attached. So again, in that object detection example, you can imagine that that soccer ball image has a label attached saying this is a circle. We know the ground truth in front, and we just want to get to that truth as much as close as possible, so that once there is an image that has no label attached, the neural network can actually predict it correctly thanks to what's been learned in the training process. And the label is in here designated as the Y. And then we have Y with that kind of like roof on the top of it, which is the actual result. So we get the label and we get the actual result. So the label can be a circle and the actual result can be, I don't know, triangle. And we want to get to that circle as much as possible because we know that soccer ball is a circle. And based on that difference, we calculate the so-called error function, sometimes being called as loss or cost function. You may heard all of those terms being used interchangeably. An important part of this process is that then we're going to use that kind of value calculated to then propagate back through the neural networks. Hence the call backpropagation, because we're using that calculated value, and our task is now to, let's say, find an ideal configuration. And we're going to achieve that by iteratively updating those weights in the, let's say, graph in our network. In the processes, there are stuff being used like partial derivations, gradients and stuff. I don't want to dive that much into detail. So let's just say that we using an error function calculated some kind of value and then using it for updating those weights. And we also taking care of updating those values according to their influence to the error. So we need to update the weights in a way so that the resulting error is being like minimized. So next run for the same input should produce less error than the previous one. And in that process, you may be wondering, based on what criteria actually we trying to find the best setup, according to what rules we should update the weights. And there is an optimization function called gradient descent. Again, I don't want to dive into the math behind, but let's just simply say that your task is to try to find a minimum value at some function. We have a function like this, and our task is to find the minimum value, which means the minimum cost function or minimum error, whatever term we're gonna use. And in general, the task is basically about reducing or reduction of that error. We cannot simply say, yeah, the minimum value is in here. We need to take some step, explore the function to see where the minimum value actually is. And to be able to do that, we need to take steps gradually at the opposite direction of the gradient to try to find the minimum value. And the size of that step is being set by the learning rate, which is another fine-tuning parameter. Two situations. The learning rate can either be too small. In that case, the whole process of training gonna take eternity, and we may actually not end up with some sensible result. Another use case, another extreme is the other one, which is learning rate too high. In that case, we can overshoot the place where the minimum is and not be able to find the optimal minimum at all. So just keep that in mind, because that's another important technique or practice that needs to be taken into consideration. Like the learning rate is another parameter that needs to be set properly, and usually you won't be able to find the ideal figure right away. You just need to try several different combinations and see what works best for you. So let's get to the demo I promised at the beginning. Let me just close the presentation. Cool. Wondering why the mouse is not working. Oh gosh. No. All right, perfect. So we can see in this picture, sorry, we cannot really see that. Just run it full screen. Cool. So we can see in this picture is again another graph of that neural network. In this case, what's different from what we saw in the slides is that we've got two hidden layers. That's basically the only difference. And we are having the same task of detecting the object and predicting what kind of shape the object on that image in that image actually is. What you can see, or I mean it's barely visible, is that kind of grid over that image of the ball. By that I just wanted to indicate that again some kind of pre-processing needs to happen. We cannot in this case just literally throw the ball on the neural network and expect some result to be generated. We need to somehow pre-process it, usually by splitting it into, let's say, a set of pixels, and each pixel is then being evaluated separately, let's say, throughout the network. So we first start with the first run. As I told you, the first run is usually like a nonsense. But what you can see in here, it's the kind of calculation that happens at each neuron level. And this is in line with what we saw in the slides. Like we need to calculate the sum from the previous layer, then we are adding some bias, then some function, which is the ReLU in this case, one of those activation functions is being called, and result is some kind of number 0.782. We're gonna run through the first run, and some first outcome is being emitted. And at that point, neural networks tries to convince us that the ball is actually a square, which we know is not true. So we need to calculate the error, as we saw in that picture. And we need to use that error to go back through the neural network, calculate the gradient, and update the weights accordingly, so that ideally the error is minimized next time, or at least is a bit lower. So you can see, for instance, in here, that the weight has been updated from 0.7 to 0.67. So we basically, simply speaking, lower the probability that the square is going to be predicted next run. Yeah, so let's just wrap it up. You can see that we made some improvement. we got better in the next run once we re-evaluated the result for the same input. But you can see that we are quite not there. And by that, I just wanted to demonstrate that it's an iterative process. It takes some time, and we cannot just get it right from scratch without any context or without running through the neural networks 1,000 times. All right, so let's just wrap this up. Three main things that I would like to take away from this session is that a neural network is not a heuristic model. There are no handcrafted rules. There are no shortcuts to ease our training. We just need to go through that iteratively, and it usually takes some resources, takes some time. It's like an expensive process. Quality data is essential. As I said, your neural network is only as good as your data is. So pay attention to what sort of data you're basically using to train your neural network. And finally, this is just the beginning. In the last 30 minutes, we just introduced that concept to ourselves. And let's say when considering production toolings, it's not just about using one neural network. It's usually a combination of those. Some advanced mechanisms or algorithms are in place. So yeah, there is some journey ahead of us, but hopefully you at least got the main concept. I'm so sorry for using the whole slot. There was so much I wanted to tell you. So unfortunately, we probably don't have any time for the QA. But I'm here for the rest of the day, so feel free to reach out to me and ask any questions.